Okay, I thought I'd record a little screencast here just to, clarify a couple of points in quite a confusing lesson earlier today. Just hopefully this will help settle some of those ideas. So I'm going to go right back and actually write up our induction proof from the homework question 2A. Just want me to do it on the board, but in the factorizing process, I wasn't pleased with the way it rolled out, so I just want to go through that again. So if we go through our steps, we test here at r equals 1, our lowest value. So we get the left-hand side to equal 1 squared is 1, and the right-hand side to equal 1/6 by 2 by 3, which equals 1. So we check that step off and we move on. Second step is to assume that the statement is true at r equals k. So what that entails is that at r equals 1, it's 1, at r equals 2, it's 4, at r equals 3, it's 9, and we're summing all these up all the way up to k, which is k squared, and we're assuming that the result is k over 6, k plus 1, 2k plus 1. Alright, moving on to 3, now we are proving true for r equals k plus 1. So we are looking at the same sum all the way to k, but now we're going to bring in k plus 1. And we want to show that it's k plus 1 over 6. So just substituting k plus 1 wherever you see k up here. So this will be 2k plus 2 plus 1, which is 2k plus 3. This is the goal. What we have now is we will work with our left-hand side, and we will pick up what we can glean from our k assumption, which is all these equaling the statement here. So we will rewrite the left-hand side such that we use our assumption and we add in our new term, our k plus 1 term, and we go from there. Now, what I did at this point, it was a little clumsy. We're pulling out k plus 1 over 6 to start with, which I reckon is just too big a leap. And there was a little bit of confusion certainly on my part as to how then it rolled out to get us what we wanted. So I think more satisfactorily from my point of view, if we just go back and pull out our k plus 1 here, which is a clear common factor. And what we're looking to do is factorize, because you can see what I'm after is in factored form. This expression here in factored form, this is not. So I want to factorize. So taking out what I can see as a common factor is k plus 1. Opening up, what have I got? I've got a k over 6 here. I've got a 2k plus 1 there. So this k plus 1 by this will give me the first part of this expression. The second part will be by just including another k plus 1 in there. So just to clarify that pair gives me this, and this distributes out to give me that. So just I'm doing all that work. Right, so now it is a tidying exercise with k plus 1 out the front. I've got this k over 6, 2k plus 1. That together is 2k squared plus k all over 6. And I've got this k plus 1 here. We would then, I think, inside the big bracket here, put everything over 6. So I've got 2k squared plus k plus, now I've got k plus 1, which becomes 6k plus 6 all over 6. So I've got a single fraction there. Now I can pull the 6 out. And inside, I just have 2k squared plus 7k plus 6. And that quadratic will factorize to 2k, and I need 3 and 2, and it's going to be the 2 there for the 4k and the 3 there for the 3k, and that is the right hand side. You then write out your explanation. since true for n equals, or r equals 1, sorry, etc. Okay, so I think I'm a little happier with that. Okay, so now going on to our inequality proof by induction. So prove, what were we doing? 2 to the power of n is greater than or equal to n squared. Now this is the one we looked at in class. It's the one that, all right, so that's for n is greater than or equal to 4, where n is an integer. Okay, okay, this is one in class where we developed it, got to a point where we then went and did another induction within the induction, which I could see was getting a little difficult to follow. So I'm going to try and do it in a way now that is still not an easy induction question. Like I said, the inequalities are the hardest, but hopefully we can do it in a way that's easier to follow. So our test case, right? So we test for our lowest values of n, which is n equals 4 in this case. So our left-hand side is 2 to the power of 4, which is 16. And our right-hand side is equal to 4 to the 4 squared, which is 16. They're equal. That's part of my inequality statement. So that is okay. We then go to our assumption case. So we assume true for n equals k. So now we're saying that 2 to the power of k is greater than or equal to k squared. We're going to assume that, and then we're going to prove, step 3, prove true for n equals k plus 1. So our task, our required to prove, is that 2 to the k plus 1 is greater than or equal to k plus 1 squared. Okay, how do we use our assumption? Well, 2 to the k plus 1 is twice 2 to the k. All right, so I can say from 2, so from step 2, 2 to the power of 2 times 2 to the k will be greater than or equal to 2 times k squared, multiplying both sides by 2. So therefore, our assumption can read 2 to the k plus 1 is greater than or equal to 2k squared. So now if we look at 2k squared, we concentrate on 2k squared. Now what happened here was that, so now we're making this assumption. So using this now in my report to prove, I now need to show that 2k squared is greater than or equal to k plus 1 squared. If I can do that, if I can show that 2 to the k plus 1 is greater than something that is greater than k plus 1 squared, then I have proved what I need to prove. So now I work on 2 to the k plus 1 being greater than or equal to k plus 1 squared. So therefore, now what I'm required to prove is that 2k squared is greater than or equal to k plus 1 squared, or that 2k squared minus k squared minus 2k minus 1 is greater than or equal to 0, or that 2k squared, or that k squared minus 2k minus 1 is greater than or equal to 0. So I'm now going to stop writing the inequality. I'm going to work with the left-hand side. Left-hand side is equal to. Now this is the point at which I, in class, went and did another layer of induction, and that is perfectly fine, but this might be a bit clearer. I think at this point we can look at the left-hand side and complete the square on it. So let's have a look at the left-hand side is k minus 1 squared minus 2. And if we look at this statement and values of k greater than or equal to 4, we can say that that is greater than or equal to 0 for k greater than or equal to 4. So therefore, and that's it. So that's going to that's probably going to annoy you because we did another whole induction, which is in a way neater, but this is obviously much quicker. We're at the point here where we just need to show that this inequality is greater than or equal to 0. And this quadratic, by completing the square on that quadratic, writing it in such a format, it just makes it clearer that when we put in values of k equal to 4 and greater, it has a value greater than or equal to 0. So that proves our inequality. So we can say therefore 2 to the power of 2 to the power of k plus 1. Therefore 2 to the power of k plus 1 is greater than or equal to k plus 1 squared for k greater than or equal to 4. So therefore we go to our fourth step. Since true for statement is true for n equals 4, and if true for n equals k, true for n equals k plus 1, by the principle of mathematical induction, it's true for all values of all values of n greater than or equal to 4. ... Okay, this is what I'd like you to do for homework. I'd like you to prove, let's have a look. Let's do this one. Prove by the principle of mathematical induction that 3 to the power of n is greater than or equal to 1 plus 2n. Now, I'd like you to have a go at that, and then we'll have a look at that in class tomorrow. Okay, cheers.